So we've looked at how to geometrically represent complex numbers using Argand diagrams and then represent the number in polar form coming from that. What I'm going to do here is I've got a couple of questions for you. I want you to read the questions, pause the video, have a crack at them, and then come back and check yours against the working I'm going to show you here. So here you go. First two, I'm just wanting you to calculate modulus and argument of the complex numbers. Make sure you follow the logic through for that. Remember the diagram with the quadrants and how we change it back to the principal argument. And then the second one, I want you to take it to one step further and actually write the complex number in polar form. So pause the video and have a crack at that. So the first one, both of these, I want you to calculate the modulus and argument of each of those numbers. So the first one is z equals 3 plus 5i. So first thing we want is the modulus of z, which we know is given by the square root of x squared plus y squared. In this case, that's the square root of 3 squared plus 5 squared. 3 squared is 9, 5 squared is 25, gives me the square root of 34. So we could leave it as square root of 34, a third if it wanted. If it asked us for a decimal one, if we take the square root of 34, we'd get 5.83 to 3 significant figures. Second part was calculating the argument of z. Now remember, for this, we do tan minus 1 of the magnitude of y over x. We ignore any negatives, but we're lucky that there's no negatives here. So the good thing is we can say that since we're just doing tan minus 1 of 5 over 3, and there's no negatives we have to take into account, this will give us our principal argument theta. So stick that in a calculator. What you get from that, remember, stick to radians, is that theta equals 1.03. Again, we'll go to 3 significant figures. So there you go. There's the first one. Argument and modulus. Second one, again, I want the modulus and argument of this number here. Modulus of z, again given by the square root of x squared plus y squared, which in this case is the square root of negative 3 squared plus 6 squared. If I do negative 3 squared plus 6 squared, what I end up getting is the square root of 45. Now, keeping it as a third, we could simplify that and write that as 3 root 5. If we then wanted to take it one step further and give it as a decimal, we'd end up getting 6.71 to 3 significant figures. There you go, that's me get the modulus of the complex number. Now I get the argument. So again, we look for the argument of z. Now, if we look at it, there's a negative associated with the x value here. So what we're going to do is we're going to calculate the argument ignoring the negatives and then correct it based on our diagram and quadrant that we're in. So argument of z here is going to be given by tan minus 1 of y over x, so just of 6 over 3 in this case. Tan minus 1 of 6 over 3, tan minus 1 of 2 gives me 1.11. Again, we're going to stick to 3 significant figures. So we get 1.11. Now if we think about our diagram, our imaginary plane, think of where the point's plotted for this one. So I've got a negative x and a positive y. So it's going to be in this quadrant here. And remember, to bring the theta to where we want it associated with this quadrant, what we have to do is pi minus the theta for that. So in this case, what I'm going to say is that fine, so my theta gives me the argument of z being pi, take away this 1.11, which in this case, if I do pi, take away that, I get 2.03 for my argument. So there you go, there's my argument of that number, and here's the previously calculated modulus. The next question, I wanted you to take it one step further and write the complex number here in polar form. Now, remember for polar form, we have to write it in the format z equals r bracket cos theta plus I sine theta. And from this, the r we know is given by our modulus of z, And we know the theta is just the tan minus 1 part that we did before the argument. So it's going to be tan minus 1 of y over x. So we calculate both of these the same way we would before, and then stick it all together. So modulus of z here, we're going to do the same as we did before, so it's going to be the square root of 12 squared plus negative 5 squared. So 12 squared is 144, negative 5 squared is 25. Add them together and you get the square root of 169. That's just 13. Then we want to look at our arguments. We want to look at theta. Now if you look at the number, originally we've got a negative associated with the imaginary part, so a negative with a y. What we start by doing is ignoring it. So we do tan minus 1 of y over x, ignoring the sign, so modulus of y over x, in this case it's going to be 5 over 12. If we then do that, stick that in your calculator, you get 0.394 to 3 significant figures. What we then do is we have to figure out what correction we have to make to bring it back into the range we want. Well, if we imagine that we're plotting it, and we're going to look at where we plot the point, we've got a positive x and a negative y, so it's going to be down here. Now, the simple correction for that one is we just do negative theta to get our argument. So in this case, the argument of z for our number that we want here, just invert the sign, and we get negative 0.394. So there you go, that's me got it. Now to write the number in polar form, all we have to do is stick all this together. So now I say fine, so I know z is equal to the r, which is 13, bracket cos, now it's a negative number, so put a bracket around that just for formatting, cos of negative 0.394 plus I sine of the negative 0.394. And there you go, that's the number in polar form. Now if you were to do cos of negative 0.394 and times it by 13, or sine of negative 0.394 and times it by 13, you should get back to this one here. Now, there will be a slight discrepancy. If I was to do the first part, 13 times this cos here, I end up getting 12.00 and then a number. So it's not bang on 12, but that's coming purely from the rounding we've done at this stage. If we were to do tan minus 1 of 5 over 12, store the answer and just do 13 times answer, we should get back to the 12. We should get back to what we want from there. Alright, so bear that in mind. Yeah, there may be a tiny discrepancy. Again, it comes from rounding. Whenever we round numbers, you lose a tiny bit of the accuracy. But that would be it in polar form because that's it. Bang on for what we want, and that is how we'd work with the argument and how we'd work with the modulus of a complex number to change it into polar form and use the Argand diagram that they came up with in the 18th century. Not bad for mathematicians who didn't exactly have access to the same sort of technology we do nowadays. Good work with them.